Good day, I'm Dr. T, and welcome to my desktop. So today, looking at different ways of understanding how the innards of the atom work, and then kind of continuing on and understanding how that affects um, chemistry as a whole. So the earliest model of the atom was the billiard ball model. That would be John Dalton's from the early 19th century. And to understand what's going on inside the atom, it's really helpful to understand how it responds to light, because that gives us the most information about the innards of the atom. So I'll go ahead and turn on my light. And with the billiard ball model, basically all the light should just kind of bounce off. But that's not the case. You know, some light goes through atoms, other light gets absorbed. And yeah, this doesn't match reality at all. Now, after the billiard ball model, kind of going more into the late 19th century, we get the plum pudding model. The idea is this is raisins in plum pudding or bread pudding. And the this is the electron. The electron was the first of these guys discovered as its own individual particle. And the idea is if they have the right amount of energy, they can bounce around the electron and in the process getting absorbed. If they don't have the right amount of energy, then they just go through. And this is actually kind of the general trend. But here's the catch. We then discover that the nucleus is a thing, and that the electron is existing, around the nucleus. The nucleus is really, really, really tiny, and all the examples here, the nucleus will be much larger than it would be to scale. So the next one would be, okay, well, maybe it's just like a solar system. Yeah, the only problem with that is the electron would either escape or crash into the proton every time, and thus that's kind of confusing. All your electrons would self-destruct. So that can't be the case. Then a guy by the name of Niels Bohr comes up with one. And this one starts actually working fairly well. We still use this a little bit. The downside of the Bohr model is it only really works for hydrogen. Now this happens to be hydrogen. And to really see what it's doing, I'm going to turn on the spectrometer. And what we're doing is we're looking at the light that's absorbed by the hydrogen atom. And what you'll notice is as this is going through its thing, the electron is circling around these shells. And that lowest shell, which is what we call the ground state, it's there when it doesn't have any extra energy. And then it can absorb energy from a photon. It jumps up to an excited state. And the excited state, once it has more energy. Then it falls back down to the ground state and in the process gives off the energy in the form of a photon. Now, it could fall back like it just did as hops. So instead of one straight fallback, it could fall back in a couple of hops. That means it would give off multiple photons and their sum of their energies would equal what it had done. Now, core to the Bohr model is that the electron cannot at any point exist in between these shells. So the spots that don't have dotted lines, the electron cannot be. It is not that the electron travels through the space, it simply ceases to exist here and exists there and then ceases to exist there, then there. So one, that's really weird, really, really weird. And two, why? What is special about these shells? The data definitely shows, if you look at the spectra for hydrogen and you shine light on hydrogen or you excite hydrogen, if you shine light on hydrogen, it absorbs photons. We call that a dark line spectrum. If you put energy into hydrogen, like run electric current through it or heat it up, in that case you get a bright line spectrum. They're the exact same spectrum. It's just, kind of a negative of the other. Yeah, so what is with these shells? Why are these shells here? And what's up with this whole not going in between shells? How does that even work? Well, this is where we get into quantum physics. And what we're realizing is that energy is quantized in the form of these photons. Light is not like a normal wave. One, it doesn't actually go through a medium. Every other wave has to go through something. Sound must go through air. Ocean waves must go through ocean. Whereas light can go through nothing, through true vacuum. And it's like, what? And then normally you just, you have a wave, the particles are moving. The energy being cut half and half and half and half in that wave. And yeah, no, light, quantize energy. It's in little packets of wave called photons. And we get this idea of a wave-particle duality. Light is both a wave and a particle. And as such, it has properties of both. And that, you know, kind of hybrid concept leads us to the photon. And that's one of Einstein's major contributions in 1905. Okay, this is weird. And yeah, moving on. So a gentleman by the name of de Broglie, and I'm butchering the guy's name, I do apologize, argues that, hold it, light is a wave particle. More wave than particle, but it is definitely has particle properties. What if electrons are too? And so this gets us into the idea of a standing wave. Standing waves, the easiest to see it is on a stringed instrument. So you grab your violin or your guitar or your piano or whatnot, and you strum, beat, bow, however you make your music on that one, and you cause a wave down the string. Now, what controls the waves on the string, which then control the pitch of the instrument, is the speed that they can travel, which is controlled by the tightness of the string, and the size of the string. The wave has to go down the string, bounce off, go back, and in a way not interfere with itself. It needs to have what we call constructive interference. So it has to, where it's going up and down, it has to meet up to up and down to down, and where it's not what we call a node, it has to have a node. Otherwise they cancel themselves out. That's what we call a standing wave. And so the argument is, well, what if the electron is a standing wave, and thus these orbitals are where those standing waves for an electron can be a standing wave. These are the regions in space that, you know, can fit with the wavelength of an electron. And this is all looking fine and good, and we still have a slight problem. De Broglie, once again, sorry for butchering his name, gets basically the why these shells are in the right spot, but he doesn't fix the other problem with the Bohr model. And that is, this only really works with hydrogen. Kind of works with helium, and that's actually how we discover helium. We see the spectrum from helium in the sun. We then match that to the Bohr model and realize that that must be an element that has 2 protons, and thus we discover helium. Only later do we discover it in oil wells in Texas. Then comes an interesting guy by the name of Schrodinger. This is Schrodinger of cat fame. And yeah, he's arguing, okay, let's fix this, and that the reason that this isn't working for the Bohr model for all kinds of elements, and by not working, I mean the spectrum isn't quite right. They're not quite in the right spots. The Bohr model would predict 1 line, where in reality you get 3 other just incongruencies. So Schrodinger's argument is that the reason you get these incongruencies is that Bohr and de Broglie basically are assuming the electron is existing in kind of this spherical shell around the nucleus. And Schrodinger's like, well, it could, but it could also exist in different shapes. And so what we're doing is we're seeing some of them now. So at this point, we are seeing ones that's more of kind of donut shaped. Actually, I think this will give me a little bit more information as to what shape we... No, it's not. Okay. This is showing which shell it's... Oh, yes, it is. Okay, so in the Schrodinger model, he's arguing, okay, you've got the shells, but you've also got what we call orbitals, different ways the electrons can exist in the shell. So this L equals 0, what we call S, is spherical. L equals 1, which is what we call P, is more of dumbbell shape. You actually can get a couple of different ways of doing P. L equals 2 is what we call a D. That is more of kind of a clover shaped, although there's a version where it's a dumbbell with a donut. 3 would be an F, which is kind of a double clover leaf. Just double checking, make sure I got the letters right. Yeah. Where, you know, like the 4 and the 5 are very rarely seen. Okay. And thus, these are actually slightly different energies than they would be the shell. And this actually works out really good, and this allows us to understand things. Now, I should caveat that these orbitals that are being described by Schrodinger only apply for an atom that's in a near vacuum, that's not interacting with other atoms. If you've got a solid or something that has bonds, or even just a dense gas, then the presence of other atoms will start distorting the way that these orbitals exist. And you have to change your understanding of how these orbitals work. There's what's known as molecular orbital theory, which starts taking this, but for multiple atoms that are sharing electrons together, what we call molecules. I am not going to get into molecular orbital theory because it is definitely it's more complicated than this, and I don't want to dive too deep into here either. But yeah, so this is Schrödinger's idea, and with this we can actually start getting some really interesting view of the periodic table. So when you look at the periodic table, you see groups and periods, and the groups are the vertical columns, and they all have similar chemical reactivity. Now, with these electrons, with hydrogen, it just has the one electron, and this is the only thing I can show you in this particular model is that one electron bouncing around. So let's go back to the Bohr model. It's a little easier to see. So I've got the one electron. Now, this n equals 1 is the ground state for that one electron. If I were to have a second electron, it would be buzzing around with n equals 1. But if I was to have a third electron, so let's say I was in lithium, then it can't be at n equals 1. N equals 1 is full. It has to go to n equals 2. So n equals 2 for lithium. So if I had 3 electrons here, that would be the outermost shell. And that's what we call the valence shell. The outermost shell with the electrons in it is the valence shell. Now, obviously, you have all these empty shells. They exist. They're not really a thing. They're a region in space. So it's not like they do exist or don't. They're just, there. Because they are there, if you get what I mean. But yeah, so the outermost shell that actually has electrons in it, we call that the valence shell. And all the inner electrons, those are called core electrons. Now, when we're looking at this guy, obviously hydrogen only has one electron. It's on the valence shell because it's only got the one. Now with Schrödinger, we can actually start taking things the next step. So with the Bohr model, what you look at in those groups is that they line up with the same number of valence electrons. So if I look at the alkaline metals, where hydrogen is, those all have one valence shell electron. Hydrogen has one electron outside, lithium the same, sodium the same. They have more and more electrons, but all of the other electrons are in the middle, in the core. Now, if I go one column over, the alkaline earth metals, these are all going to have 2 electrons in their outer shell. So they all have 2 electrons in their valence shell. I'm going to ignore the dip in the middle. Those are transition metals. They're doing something a little bit interesting. I'll get to that here in a minute. Now, if I go over with boron, that's got 3 electrons in its outer shell, carbon 4, and so on and so forth, all the way to 8 for your noble gases. And the chemical reactivity is heavily controlled by that outer shell of electrons. Therefore, that's why they're in their group. Those groups were set by chemical reactivity, and, well, they have similar chemical reactivity because they have the similar valence shells. Now, looking at Schrödinger, turns out these guys are also going to have a play in these orbitals. We can break the periodic table into blocks, and in doing so, these are going to be blocks where that valence shell chemistry is going to be influenced heavily by a particular orbital. So the alkaline metals and alkaline earth metals, the first 2 groups, those are dominated by s orbitals, or this L equals 0. And thus they have similar chemistry because of that domination by the s orbital. Once you skip the dip in the middle, go over to that second block, ignoring helium. Helium actually belongs in 2 different spots on the periodic table, depending on how you think about it. And in this case, it's better off represented next to hydrogen than all the way over where it's at. This kind of square area is known as the p block because that tends to be dominated by this p orbital because it has just slightly different chemistry than the s orbital, and it's going to kind of come into play much more for those atoms in that area. The dip in the middle is called the d block. Its valence shell is actually very similar to that of the s block, but it has d orbitals in the shell below it, and that would be this kind of 2-1, and those play much more of an important role in the chemistry of d block elements, and they can do some really interesting creative things. This is also why they're called transition metals. And so this kind of bordering area, they're transitioning from your alkaline earth and alkaline metals are transitioning over across the periodic table, and they do some really interesting chemistry, and it's because of that d orbital. Now, down at the bottom, you have the rare earth metals, or the lanthanides and actinides, depends on how you wish to call them. In reality, they don't actually belong there. They belong up in where lanthanum and actinium are. But most periodic tables don't have it like that because it's really awkward to draw, and their chemistry is all fairly similar. For these guys, we call them the F block because their chemistry is at least in part dominated by the F orbitals of actually 2 shells below the valence. Turns out that the energy of some of these orbitals changes enough that they actually affect when they're not strictly the valence shell, because they're out far enough from the nucleus that they may as well be valent. So it's this kind of weird chemistry with these guys, which as a biochemist, I'm glad I don't have to deal with these very much. But if you're doing inorganic chemistry, etc., the chemistry of these metals, it's definitely a lot more complicated than the chemistry of carbon. So yeah, we've got our different regions, we've got our different blocks, and understanding where on the periodic table you are can give you just kind of a generic idea of what's going on, and give you kind of a nice clue as to the way these are going to behave. So with that said, actually I do want to bring up the S, P, Ds, and F one last time. For your S orbitals, you only get one of these. So you get one S orbital per shell. The p orbitals, or the 1 orbitals, even though it's only showing one block here, you actually get 3 orbitals per shell. And this is going to be very important once we start looking at how things bond, is the number of orbitals. Each orbital holds 2 electrons. So over here you got 3. The Ds you get 5. The Fs you get 7. And if you look at the size of those blocks, that's going to represent how many electrons you can fit into these. So if you look at the S block, it's 2 wide. There's 2 electrons going to be put in S orbitals. If you look at the P block, it's 6 wide. There are 3 orbitals, therefore 6 electrons can go into it. Count your transition metals, that's the D block. There are 10 of them in a row, and thus there are 10 electrons, and that's because there are 5 orbitals, each one holds 2. Count the rare earths, and it's 14 long. Once again, 14 electrons can go in there because there are 7 orbitals. I will point out that some periodic tables will put 15 on that alkaline earth because there's actually a debate as to which one is in there versus the transition metals. So sometimes you will just see a blank in the transition metals and then 15 in the rare earths, because it's either the one right at the start of the row or at the end of the row that actually goes in the transition metals. We just have not agreed upon which one is which. It's trying to understand how their electrons are behaving, which would set that up. Okay, now with that said, have a wonderful day, and I will see you in later videos.